So our second speaker today is also from Heidelberg University. We're very happy to welcome Professor Peter Fischer here today, who will tell us about the detection of photons with CMOS detectors today. Let me briefly say a few words to Peter. Peter received his PhD in physics in 1992 at Heidelberg University, and afterwards he joined the group of Professor Norbert Wermes here in Bonn, at University of Bonn, where he contributed to the Atlas Pixel project, the chip design for the Atlas Pixel detector. And it's especially nice for us to have you here today, because you were one of the people that helped setting up the Silicon Lab that was built up and founded by Norbert Wermes, and at the Physics Institute, which has recently moved to the FTD. So you can now look what has become of it by just going up to the second floor. So very nice that you're here.
See that these initial works, that this is still going on, and it's growing, and it's having success. And I think the work here is really known in the world. There are really some big experiments benefiting a lot. And so this new building is a merit and a recompense and a Verpflichtung, of course, to move on.
I agree.
So thank you.
So I'm not quite done yet. Sorry. You're not even a professor yet in my. In 2002, Peter became full professor at the Institute for Computer Engineering at the University of Mannheim, which I think 6 years later or so was transferred to Heidelberg University, so the institute and your group as well. Peter is developing electronics chips, specialized electronics chips for the detection of particles, for very, very small signals, and applications of those in fundamental physics, in synchrotrons, also medical applications, so wide area of applications. In the last years, you focused quite a bit on the detection of single optical photons. They have potential applications for dark matter searches, for instance, for electron microscopy, for hadron therapy, and so on. And I think this is what we'll hear about today, and we're looking forward to your talk. Thank you.
So I haven't been here for too long time. It's really a beautiful town. It's so green, and I didn't realize this when I was here. But if you are in other towns, you realize there's so many trees, so many parks. It's really wonderful. And in a different universe, when I didn't get my position in Mannheim, I would still work in this nice university and in this institute. Maybe my lab would be up there. But then you wouldn't invite me for the presentation. So it's. So I'm going to talk about photons. And when I write photons, I mean optical photons, light. And this may be a surprise for the people who know me, because I have been working on particles, detecting particles with silicon detectors for quite a long time. Also in large experiments like Atlas, as it has been mentioned. And I made a few observations. One observation was that it's because these experiments are getting bigger and bigger, apart from the sociological issues, they are really big tanker. And it's very difficult to change things. So they have to work according to the principle, never change a running system, because you have to make all these big systems work. So it's very difficult to bring in new ideas. And it's even more difficult if you are a small group, a one-man show somewhere in Heidelberg, in a small institute. You really have to have a certain size to have enough impact to convince people to change things. So this is difficult in this world. The second observation is that I was always looking for applications beyond physics. And there are applications, of course, like what we will hear, but particles mustn't be detected everywhere. So particle is a special thing. Light is much more important. Light is everywhere. So light detectors are quite interesting. And the third observation was, it's surprising that the physicists, they develop a lot of particle detectors really themselves. They design the PN junctions and so on, but they buy the photodetectors. Photodetectors, you go to Hamamatsu, to the catalog, and you buy them. You design some readout electronics, but I find the investment to find new photodetector concepts or applications or architectures, it's much less. So there was room there. So this was one of the reasons why I started this enterprise. There was also a chance coincidence, because I presented a talk on a conference on silicon photomultipliers, classical silicon photomultipliers. And there was a person from Fraunhofer Institute from Duisburg, and they made avalanche photodetectors. And they kind of offered me to use their technology to make CMOS chips with avalanche photodetectors, which will be the topic of the talk. So this was a coincidence that I got access basically to this technology, and that's what I'm doing since 5 years or so, since 10 years roughly. And I want to talk a little about this because it's also a little bit different from the normal particle detectors that you're doing here. Now, up or down? Down. Good. Okay, so why detect optical photons? I think that I don't have to convince you that optical photons are everywhere. So you have the normal cameras. You have cameras for low light, so you have to be very sensitive. You have few photons, for instance, from fluorescence in cells. You have few photons from particle physics, collisions, effects, and so on, or you have photons from atoms in traps. So there are many applications where you need to detect photons, and very often you have to be sensitive. Now, to give us an idea how many photons we want to see, I made some small calculations. So how many photons do we have? And if you divide the solar constant by the energy of some green photons, you can find out that on 1 square millimeter of area, in 1 microsecond, you have still a very large number of photons. So this is really a continuous stream of photons. If you have a normal light bulb, it's already less. I found numbers on the number of photons at full moon, still 5,000, and even at a dark, cloudy new moon night, you still have 3 photons per microsecond on a square millimeter. So these are still millions per square millimeter. Yeah? So the detectors we are going to see, which can see individual photons, they are really sensitive. The second introduction is, what is the sensitivity of a human eye? So I'm not expert, so I looked this up. So you probably know that the eye has 2 types of color detectors. There are the Zapfen, which are not so sensitive, but which can distinguish colors. And humans have 3 different types. And it's interesting to see that other animals have less or even more. Yeah? And when reading this recently, there is the famous, there's a shrimp, which has eyes which move like this, the Fangschreckenkrebs. And it has 10 or 15 chromatophores. But now they recently find out that it cannot even distinguish blue from red, because they have the chromatophores, but they're not correctly wired up in the brain. So the number of color, and also I learned, this is a side remark, because they are on the X chromosome, women have better vision, color vision, than men. So the Rot-Grün blindheit is very much famous for men, and women sometimes have 4 chromatophores. So I think this is the reason why women have better color taste, probably. Yeah? Okay. But okay, I have to speed up. So then, there are the rods, which are much more sensitive, and I was really impressed to see that such a rod can actually create a nerve signal, a pulse, which you can probe with a needle for a single photon when it's absorbed. But only 10% of the photons which come in the eye are actually hitting the rods. And because a single spike on a nerve signal would be interpreted as noise by the brain looks for more, looks for bursts, and roughly you need 10 signals so that the brain thinks there has been a photon. So if you put a person in the complete dark for hours, and then you shine little light, then with some confidence level, the brain can detect 100 photons. So that is, and I'm still impressed that this is really a low limit. Yeah? Okay, now, but we want to detect photons with silicon. We are still in the silicon world. So at some point, we have to absorb the photons with the silicon. So if we have a piece of silicon and photons go in, first observation is that the interaction of the photons with the silicon depends on the energy of the photons. And we are really lucky that the energy of visible photons is just in a good range for silicon. Not optimal, but a good range. And if you have a blue photon, which has a short wavelength and a high energy, it can ionize atoms immediately. So this is why blue photons, they don't penetrate deep in the silicon. They are absorbed at the surface at roughly 1 micron. On the other hand, the red or even infrared photons, they have very low energy, and they have a hard time to ionize the atoms, and eventually, if they are too infrared, they will go through the silicon. Silicon becomes transparent for infrared light. That's a pity, because many technical applications use infrared light, like telecommunication, yeah, or LiDAR, yeah, because you want to use laser light, which is not visible for the eye, and you cannot use silicon for this process. But the message here is that the silicon is quite good for green light, because the penetration depth is reasonable, let's say. Yeah? And by the way, there are detectors which measure the absorption depth of the silicon and then can infer the color of the light. Yeah? Okay, now go back. So this single photon, we are talking about a single photon. It can be absorbed, and when it's absorbed, it ionizes a silicon atom, and I have an electron. Now I have to see this electron. But the electron is somewhere in the silicon, and the first thing I have to do is to bring the electron to an amplifier, to collect the electron. So I need an electric field, and that is a problem, because if I apply a voltage on silicon, on naked silicon, a current will flow, because silicon is a conductor. It's not a good conductor, it's a semiconductor, but it's conducting a little. So I will never be able to see this single electron in the current that is flowing anyway. So here we need a first trick. And this is the magic of doping. So this is quite on an introductory level. I was thought I should talk a little on an introductory level. We're coming to the more complicated stuff later. So silicon is 4-valued, like carbon. And if you grow a perfect silicon crystal, every silicon atom has 4 neighbors, and all the electrons are eaten up. So you basically have a perfect silicon lattice with nearly no conductivity. I've drawn this here again, and now there's a fun fact. You see in all the books, you see this picture of the silicon. Yeah? So this is a 2-dimensional picture of a 3-dimensional structure, where you would say you cannot catch everything, because somehow you're missing a dimension. But the important message that every silicon atom has 4 neighbors is perfectly caught here, so the topology is right here. So I find it surprising. Yeah. Now, so as I said, basically all the electrons, they're used up, they're bound here. And now you do this doping. You mix a small fraction of atoms with 5 electrons into the silicon. They're called dopants or donors. And these atoms, like phosphorus, for instance, they will use 4 of these electrons in the bindings, but the 5th electron has no place to go. So it will basically not stay with the atom, it will move around. And you have created a funny material which is called an N-conductor, where electrons are free to move around. Yeah? And by the way, when the electrons move away, the positive phosphor stays in place. So when you take away the electrons, the silicon will charge up positive. Yeah? And you can do the same, of course, now naheliegend with 3-valued atoms. Then it's a bit more tricky, but effectively what you have a positive charge moving around, which is not really a charge, it's a hole, but it looks like a charge. Now this is a doping, and then you can bring these 2 structures together and construct a diode. And I changed the title of this slide from the PN diode to creating field without applying a voltage, because that is the trick you're doing here. So when you bring these 2 substances together, then the electrons from the N-doped material will move away and fall into the holes of the P-doped material, and you will have a positive charge left on the right side and a negative charge on the left side. Yeah? The electrons fill the holes here. Fill the holes means they basically satisfy this boron atom, and they give it the electron it needs. Yeah? So there's 1 electron too much here. This is why it's negatively charged. Yeah? And then, because you have charges, then Gauss' law tells us when we have charges, we have to have electric fields, and you have an electric field without applying a voltage, magic. Yeah? And this electric field is the field we need to collect now the charge that we have created by our photon. Yeah? And this is called the depletion region because there are no more charges around. All the charges have been eaten up by the holes, if you want. And this is important to have a region which is completely free of charge carriers because we need to detect one charge carrier. And so we have to clean up everything. Yeah? So the structures then look, this is a typical silicon detector still, yeah? So this is how the structure then looks. I have an N doping and a P doping. Yeah? So the junction I mentioned, this depleted region is here. And when I apply no voltage, I have a depletion region, I have a field, but maybe it's not so good, it's not sufficient. I still can help it by adding extra voltage. And without going into detail, you believe me, the depletion region will grow. And when now I deposit a charge in this depletion region, there's this field there, the electron will drift to one side, and when I put an amplifier there, I can see the signal. So this is how I collect the charge. And I have made a simulation here to show how this looks in detail. So if there's a junction here, so this is the depth in the silicon, this is the doping, there's the NP doping junction here, and there's this field which is created by this magic effect, and there's a depleted region, there are no charge carriers here. And here I just want to show that if I increase the bias voltage, then of course the depletion region grows and the field grows. Yeah, and we will need the same plot later for the avalanche device. Yeah. Now, okay, can we see a single photon? We have the photon, we drift it to the electrode, and we just have to see it now. But what is the signal that we see? So it's the same signal argument. Yeah? So unfortunately, the charge of one electron is very small. It's the elementary charge. Yeah? And if you see this charge, now it's not on a heat capacity, it's on a capacitor. So this charge will produce a voltage on a capacitor. So we have to put in some capacitor value, and I put a small value, 50 femtofarad, and this gives a voltage of 3 microvolts. Same argument, this is too small. Yeah, we cannot see it. We could reduce the capacitance, of course, to increase, but it's too small to see a single electron. To be more precise, of course, if we had an amplifier which can amplify this, no problem, but every amplifier has noise, and it turns out that you cannot have an amplifier with such a low noise. It's a big shrunk, yeah. So the noise of charge amplifiers is coming close to this, but one electron is really hard to get. So a detector which just collects the charge and then amplifies it is not feasible. So direct detection is really hard. So we need another trick. And the solution is amplification, of course. And I said external amplification is not so easy, it's too noisy. There is a trick of internal amplification. So you put the amplifier in the device, it's electronic amplification, but the trick is that the capacitance of this amplifier is so small that the signal gets bigger, the voltage signal gets bigger, and you manage to see it. And one device doing this is the famous DepFET devices, where we have worked for a long time, which has been mentioned also. It's very popular here in Bonn, but still one electron noise on the DepFET is still hard. Yeah? So this is not the way to go. So the obvious way to go is, of course, the experts know it, is to do an amplification in the detector itself and to create several electrons from one electron. So you need, like a Geiger detector, you need a physical amplification. You have to produce an avalanche. You take this electron, you drift it, you accelerate it, and you hope that it creates another electron hole pair and so on, and you get an avalanche process to get a larger signal. Okay, so we need a large field to do this amplification. So we could just crank up the voltage on the detector, but it turns out that the fields we need, they are so high that we cannot get these high fields with the structure I've shown you. We need another trick. And the trick is already hidden. I have shown you that the electric field between the two doped regions, it comes from the doping. If I have a strong doping, I have a high space charge, and the high space charge will lead to a high field. So the trick is that strong dopings lead to high electric fields. And so what you do is, instead of having an NP doping, you have a strong N doping and a strong P doping close by, and because the space charges here are so high, you will then also create a large electric field. And then you have to tune the device such that this field is high enough to do amplification of the electrons when they go there, but not too high that you have a spark, basically. So this is the tricky thing, to get the dopings here right. And of course, you have a knob still. This is the external voltage, because you can still increase the external voltage, increase all the fields, and then hopefully just reach the amplification situation. So this is a bit delicate, but of course, this is well known, and this works. I just want to show again this simulation. So this was the pin diode, yeah, with the normal junction here. And then we move to the avalanche diode, where we increase the doping here. So there's a strong doping on the one side and a strong inverse doping on the other side. And the consequence is that I get a very sharp, very high field. So if I go back, sorry, the field here was in the order of 1 volt per micrometer, and here it is 20 times more. And if I then even apply a bias voltage, I can crank up this, sorry, diese Bedienung ist nicht intuitiv. I can increase the field, and as I said, I just have to reach a field which is just good for amplification, but not too high. And by the way, there is also a depleted region. You see here on this plot, you see that it's depleted here. And if you increase the voltage, you extend the depletion region, and you have a deep depletion region. And in this part here, you can now absorb photons, produce a single electron, drift it to the amplification region, generate the avalanche, and then see the signal easily externally without even an amplifier. Because you give all the burden to amplify the signal to the device. So these are then the silicon avalanche detectors. And the way they are produced, you now understand this, hopefully. So you have a structure. If you look from the side, it's a silicon material with some doping. Let's say it's an a weak N doping. Then you put a strong doping layer here, and then you cover everything with a P. And the avalanche region will be here, and the collection region will be below. And you illuminate this with light. Then coming back to the colors, the blue photons will be a bit difficult because they may absorb in the P, but we have to go here. We have to go basically below the amplification region so that we can drift up. Yeah? So we will be fine for green, and we are bad for red again. Yeah? For red, we have to apply a lot of voltage to have a thick depletion. Not as thick as you need for particles, yeah, because for particles you want several hundred microns. You need 10 microns or so for photons. Yeah. And these are the devices you can buy from some vendors. And you can even buy very much larger devices. And this is a device which we actually used when we were in Bonn. Yeah, 2,000 euro avalanche diode, 100 meters from here. And the problem of these devices is you can imagine that it's really delicate to get the voltage right. Yeah? If you have it too high, it sparks. If you have it too low, you don't amplify. It's very tricky. It's temperature sensitive. So we actually made a circuit which controls the voltage as a function of dark counts and so on. So there are lots of drawbacks of these devices. So they are not really so popular anymore. And there was an idea to improve the problems that you have by segmenting the detector. So a big problem of this detector is when you have a spark at one place, the device is dead, or it has a dead time at least. Yeah, so you cannot see a signal for a long time. Another problem is that you in principle you want to operate the device at a very high avalanche amplification, but then you don't know how many primary photons you had again. Yeah? And these problems are solved by this famous silicon photomultiplier. And the trick of the silicon photomultiplier is that you have avalanche diodes, as I showed them before. These are really small, and each diode has now its own quenching resistor. And this resistor makes sure that when the diode breaks through, when you get the avalanche, that not the whole area basically collapses, but only this node here discharges, and all the other devices, they don't even see anything. So if you put one photon on a place, one of these cells fires, and the other cells, they stay quiet. Yeah? And then you can really crank up the voltage to operate everything in the Geiger mode, and you get nice signals on the individual nodes. Now that's nice, but the problem is you have a signal, a fantastic signal on this node, but you normally look at the device on these pins. But on the pins, you don't see the signal. And I don't go into the details, but that's a bit problematic. And the signal you see here becomes smaller and smaller the more of these detectors you put. So we are unlucky that the signal here is really 3 to 4, 5 volts, 10-volt signals for one photon. But the signal you see at the pins are millivolts. So you still need an amplifier. The primary signal is very big, but you still need an amplifier. And that's quite frustrating. Yeah. So what can we do? Maybe I skip this. So is this ideal? These silicon photomultipliers. So first, these are big devices. They have no position resolution. They only deliver small signals, unfortunately. You need an amplifier. It needs power. It needs bonds, cables, and so on. And the systems are complicated. Yeah. And tricky things, as I want to present them, they cannot easily be done. So what is the way out? And the way out is to do these parts in a CMOS technology. So CMOS technology is a technology which is normally used to produce chips. So you have transistors. You can do electronics. And in principle, you can ask, why can't I merge both types of devices, transistors, and these avalanche diodes? Yeah? And this has been tried for many years by many groups. In principle, it can be done. The problem is that the quality of these avalanche diodes is lousy, because the manufacturing process is not really trying to optimize this. And there are few vendors who really make an effort to get the avalanche diodes good. And this is what I said at the conference. The Fraunhofer people, they have really excellent avalanche diodes. And so they offer a process where you can have CMOS transistors and very good avalanche diodes together. But you have to do chip design, basically, to build your detector. So it's a different world, and this is why not so many people are doing this. You know, there are some groups around, of course, who do this, but not so many. And now I want to talk about this. So how does this look like? This is a typical pixel of such a detector, where you can see a big avalanche diode, or two, and then you have some electronics. So we have the avalanche diodes to detect the photons, and then we have transistors to do something with the signals. And the nice thing is here, you don't need an amplifier, because here I have a 3-volt signal. I even have a clamping diode that the signal is not so big to destroy my transistor. Yeah? Yeah? You also see a problem, of course, that I'm using some of the space by the electronics, so this device is not fully sensitive. This is a no-go for a particle detector, but for photons, you have lenses and stuff like this, so you can bring the photons to the pixels. So this can be solved. Yeah? But still, it's a challenge to squeeze the electronics into a very small space, and this is something I like. Yeah? I was always happy in Lego that I didn't have everything, but I only had my small Lego box, and the challenge was, can I build this car with what I have? This was the challenge. If you give me whatever I can get, it's boring. Yeah? So you really have to find tricky circuits to squeeze the electronics, to have a decent fill factor. Wie lange habe ich denn eigentlich? Wie lange darf ich denn eigentlich noch reden? Okay. Okay, yeah, wonderful. To squeeze the electronics so that the fill factor, so that's the fraction which is photosensitive, is okay. Yeah. And this is for the experts. So if you look at this is poly. If you look at the poly, there's not so much more poly you can fill in here. So this is for Hans. Yeah. So this is all handcrafted. Really, you push the transistors until you basically squeeze everything as much as you can. So then, going from this cadence plot to larger arrays of pixels, you can here see photographs. So this is one chip where the spot here is sized and the electronics is here. This is another chip where the electronics is improved. Spots get bigger, so the fill factor is better. And this is a number I'm proud of. It's 55% fill factor. So more than half of the area is really photosensitive. And for some, this sounds little, but even a silicon photomultiplier you buy from Hamamatsu is not 100%. They also have these resistors and so on, and they have 70% or something like this. It depends, yeah? Most people think SEPMs, they are 100%. They're not 100%, yeah? So we are getting close. We're not so far away. And this was always a no-go argument. Yeah, you have poor fill factor. Yeah? So fill factor is not so bad. Now, this is maybe a bit too technical, just to give you one idea how these circuits look like. So as I said, we're really trying to keep it simple to save transistors and space. And this is an example of one of the first chips we made. This is a chip which just takes picture, which takes images. So every pixel should be read out. That's the idea. So you want to make a chip, 2D chip, 2D array, and you want to read out. So, but then you have to say, what does it mean? How do you read it out? And one way is really to do like a camera does, a frame readout. So I set all pixels to 0. I wait for a certain time. And during this time, a photon which hits a pixel can set a flip-flop, set a bit, 1 or 0. And then I read this binary image out, and I get an image which has 1, 0. Whenever I had a photon, I have a 1, I have a 0 for no photon. I have no multiplicity, but I have this image. And to do this, you need certain infrastructure. So we have here the avalanche diodes. Then we do a trick. We do an AC coupling, which is quite unusual, but this increases the fill factor. Question for the experts for later. Then we have some masking possibilities. There's always the danger that one of these spots is broken. It's too noisy, and we can switch it off. We have basically an inverter to make a nice CMOS signal. And then we have a flip-flop, which consists of 6 transistors or so, which we can then set. So we reset the flip-flop before we start. Then we enable here a gate, an AND gate, and when a photon arrives during that time, the flip-flop is set. And when we are done, we load the flip-flop content in a shift register, and we shift it out. Very, very simple. And it should be simple because we want to have fill factor. And this works. So we have made several chip versions of this. So these are 2-dimensional imaging chips, which can see the single photons in these pixels. And we have order of 100 by 100 pixels of roughly 50 by 50 square micron with a fill factor of roughly 50%. If you scan a laser spot across this detector and you measure how often you respond, we were really pleased to see that we exactly find the sensitivity which corresponds to the area. So these spots, they don't have inactive edges or so. You could maybe find that they are only really sensitive in the middle. And this is persistent for all the chips we have. The response is really nicely flat. And I show you one first application which you will like. We have been working on PET for a long time because these are particles, more or less, not really. And the way you detect the gammas, the high energy gammas in PET is you absorb them in a scintillating material. They produce photons, and you look at the photons. And the normal way to do it, you have the scintillator, you have one of these avalanche silicon photomultipliers underneath, and you see a click. Yeah? And sometimes people try to get some position resolution by segmenting the scintillator into small needles, and then to measure the position where the light comes out. Yeah? So we have bought some of these scintillators, and look at this one. So these are long needles of this crystal in 0.5 millimeter pitch. And if I now put this on our detector, then we can, and we take single events. So these are single events where we see photons coming out. And every red cross is a spot which has fired for one particular event. And if you superimpose all these events, you can see the grid structure. You can draw these lines, and you can really see how the events look like. And you could do some interesting physics. Yeah? For instance, these type of events happens quite often, and these are Compton scatter in the LYSO. And so the gamma is absorbed in one crystal, but it's not absorbed, it's kind of scattered partially, so it produces a fractional signal, and there's still a gamma continuum moving on. And then eventually this residual gamma is absorbed in another crystal. And this is a problem because it degrades the spatial resolution. But with such a detector, you could eventually try to reconstruct these Compton scatters and improve the resolution. So this is a nice example that this imaging performance, this imaging possibility, really gives you quite some opportunities to do new things. Yeah. Now, how good are these spots now? And I've just two quantities. One is the quantum efficiency. And as we have now discussed, it peaks in the green, and it reaches a value which is completely compatible to other devices, close to 50%. Another very, very important property of these devices are the dark counts. Same as the rods in the brain, the nerves will fire from time to time, even if there is no photon. So there is dark noise. If you put the detector in the perfect dark, there are still, from time to time, discharges coming out. And this is not so little. So here are the dark counts in area as a function of temperature. And at room temperature, we have 50,000 discharges per square millimeter. That is a lot, and that is the same for commercial devices. For SIBMs from Hamamatsu is roughly the same number. So 50,000 per square millimeter is a lot. So it's hard to see the moonlight with this at room temperature. But the good news is, if you cool it down, because the thermal excitation of electrons goes down rapidly, the dark count rates, they go down really a lot. And some of the applications we are investigating are at really cold temperatures, at liquid nitrogen or liquid xenon or liquid argon temperature. The devices still operate nicely. They still work. You can just dip them in liquid nitrogen. They just work. And you get dark count rates really close to, I'm conservative, less than 0.1 hertz. So 0.1 click, one click every 10 seconds on a square millimeter device. So you really go down hard. And this was one result of an optimization process. You see several curves here. The original process we got from Fraunhofer is the blue process. It's not so good. And for the experts, there is a thermal contribution which is going down exponentially. And then there's a floor which comes from tunneling. And the tunneling depends on the field details. And this tunneling effect you can in principle improve, and they changed some doping profiles in the devices, and they brought down the tunneling really a lot. So the tunneling is much better. This is what all the vendors are now doing for these low temperature experiments, because the dark counts don't go down as much as you would like to. You have to fight this tunneling effect. Yeah. So these are really excellent devices at cold temperatures. At room temperature, it depends on the application. Okay, and the last part, I want to show you now a little what we did, what architectures we have built. So we have made an engineering run in Duisburg some time ago with lots of different chips. And I will very briefly just show 4 different architectures which are very different for potentially different applications. Very, very short. So one chip is, we always want to see the photons. Yeah? The question is, how do we read it out? And a very common application is that you have very, very few photons. So it makes no sense to take images, and the images are always empty, and from time to time you have 1 photon or 2. Makes no sense. And you can go back to the good old XY readout as we had it many years on silicon strip detectors. Yeah? If the multiplicities are low, a strip detector with crossed strips is perfect. It's very simple, and it gives you timing. So the architecture here is, sorry, wrong key, is very simple. So we have the avalanche diodes here, and when they fire, they send a signal horizontally and vertically. We decode the signal, and we generate an address. So the chip just sits there, and then it says, I have a hit in X, Y, so and so. And this whole process takes 20 nanoseconds, then the hit is gone, and we are ready for the next hit. So on this array, we can take 50 megahertz of photons, yeah? which is already quite a lot. And in many, normally when you want to detect single photons, you don't have so many photons. The application where you have 50 million single photons is rare. Yeah? So this is a very primitive architecture which gives a very nice fill factor because it's so simple. And it gives time resolution because the click here coming out has a one-to-one relation to the event here. It's only given by intrinsic limitations of the spot and the cabling and so on. So we have 100 or 200 picoseconds of time resolution. And I think there are lots of applications for this. We are looking at fluorescence imaging. We are looking at electron microscopy, where you have secondary electrons. And for these events, you want to know when the photon arrives. So the XY, this frame readout I've shown you doesn't tell us when the photons arrived. They arrived sometime during the frame, but here we know exactly when the photon arrived. Another application which is very, very popular today in many applications, and we are doing this basically for fun because other people can do better, is LiDAR, is ranging. So you have a fast light pulse which you shine on an object, the light comes back, and you want to measure the time it takes until the light comes back, and from the flight time you can infer the distance. Yeah? And you can use this to do range finding and to do 3D mapping and so on. And what you need is, you need a time-to-digital converter in every pixel now. We want to do flash LiDAR. So in every pixel, we need a small TDC with a good time resolution. And that is an electronic challenge. Yeah? You have 30 transistors, and you should make a TDC with 100 picosecond time resolution. And we have one, and it has 30 picosecond time resolution, but it has a lot of, it has only a range of 2 nanoseconds. It can only time for 2 nanoseconds, then time is over, we have to start again, and so on. So this is another application. It's more standard type. Everybody building spot detectors wants to make a time-of-flight detector. A bit more interesting, and now more coming back to physics and also to larger experiments, is an experiment for dark matter search. There are many of these experiments now around which look for rare events in liquid scintillators. So you have a big tank filled with a scintillator, and usually you have to take something which you can do extremely pure, and this is why you take noble gases. And to have enough density, you liquefy them, you cool them down, so you can, in principle, take neon, argon, xenon, krypton, whatever. And there are reasons to take one or the other. And a very popular material is xenon, which is very expensive, but which has some good properties for this. So the experiments are just a big tank of 2 by 2 by 2 meter or so. And then you hope, like in the big Kamiokande I've shown in the beginning, you hope there's an interaction and you get some light and you want to measure the light. So you have to cover 10 to 20 square meter of area with single photon detectors. And the typical detectors used today are classical photomultiplier tubes, but they have lots of drawbacks, and people are looking into silicon detectors. And so we are trying to play also in this game. We say we have nice low dark counts. We have demonstrated that. So we can give you a detector which doesn't need electronics, which has the readout all included. Yeah, you get everything. And so we have made test structures, and we have characterized these test structures. And at the moment, we have designed this chip, which looks really boring because there's a lot of blue. And the blue is the sensitive area. So this has now a fill factor of 77%, which is important in this application, yeah, because I have to see the photons. Yeah. So we have 77%. We have only very few control pads, only 4 logical signals, so that we can build modules with this chip, if it works, with a very nice fill factor and so on. And we are trying that the collaboration is not too big and we are not too small to maybe change the tanga from the PMTs to this. So this is still ongoing, and in fact, the submission of another engineering run is planned in a few weeks, again in Fraunhofer, and this is the main project on this engineering run. This is where the money comes from. And the last chip is now closing the loop, because I read, no, where is it then? I read on your slide that you're doing fiber tracking or calorimetry with scintillating fibers. And we have made a chip which is made for readout of scintillating fibers. And here the motivation is it's not the colorimeter, it's tracking. Scintillating fibers, now to explain what's shown on the slide. Scintillating fibers are used, for instance, to measure the tracks of particles. So what you do is you construct a curtain, basically, of these scintillating fibers. Yeah? And when the particle goes through, you produce light, again, in the scintillator. The light goes through the fibers. The fibers are brought out to some control room, and there you have plenty of fibers coming out, and you want to see 3 photons coming out of fiber number 5. Yeah? For instance, in LHCb. And the way this is done at the moment, to keep the order of the fibers correct, is a big effort to wind these fiber mats and so on. And then the fibers are positioned onto commercial SIPMs. So these are the classical SIPMs from Hamamatsu. They're organized in columns. And you place the fibers exactly at the right place so that you know who is who. Yeah? And then you need a readout chip. That's a Pacific chip on LHCb. And you have Photons to connect the SIPM boards with the Pacific boards and so on. So it's a typical particle physics detector. Yeah? And I think it's too complicated. So the idea is now, let's make again another 2D array of single photon avalanche diodes. And we will later place fibers on it. But we don't know where we place the fibers. We just put them at some place. And we tell the chip by programming it somehow, oops, wrong button, by programming it that all the blue spots, they should belong to one group. Yeah? So the chip is blanco, and then I program all the blue spots belonging to one group. And this group will then give me an output signal which tells me in this group I had 3 photons. Yeah? So I try to find the fibers, some algorithm, I program the chip, and then the fibers can have any size, any position, and I read this group. So it's a group readout architecture, and we have made a chip for that. So there's an array of fibers here, and this time the electronics is on the side, because, again, fill factor and electronics too complicated. That's a bit more tricky. Yeah? So we have a 1 millimeter active area and a 5-6 millimeter width. And we can put the fibers then on this device. And this was the picture on the introductory slide, and I have to take one without the dust. You have a better clean room here, probably. So this is a typical size, yeah? And then we just stick with, okay, this is just to show that it works. The way to do it, everything has to be simple. The number of photons is pulse width coded. So if I inject 1 photon, I get a pulse coming out which looks like this. For 2 photons, 3 photons, 5 photons, I get wider and wider pulses, and that works up to, let's say, 20 photons. It works quite well. Again, we don't need 100 photons. So we'll never have 100 photons. And then this is the work done at the Fischer-Karls-Institut, because I'm Technische Informatik, you know, I don't have a Drehmaschine or radioactive sources. So this is a student at the PE, and we made this cover with the fiber, and you can see the fiber. And then they put one of these ribbons they have from LHCb on top of the chip, and you can see the individual spots of the light coming out. And this can certainly be optimized and improved, but it shows that in principle this concept works, and we have a decent time resolution of 400 picoseconds or something like that. We have a good spatial resolution, and we now have to convince. Okay, summary. Photon detection is needed everywhere, much more even than particle detections. I'm a big fan of these CMOS spots, mixing electronics and spots, because you can really tailor-make your system, target-specific readout architecture. If you're done, it's a very simple system. You don't need detector, wire bonds, electronics, cooling, and so on. It's all in one. And you can get nice spatial resolution, time resolution, low power, maybe low cost. So I think this is a really potentially interesting technology for future experiments, and I'm trying to convince people. And I'm having great fun here. Yeah, I hope you see this. So it's basically bottom up. I'm making the chips, and then I'm walking around and say, who wants? So it's not so much driven from one experiment. It would be too narrow. Okay, thank you.
So thank you very much, Peter, for this inspiring, colorful, and entertaining presentation. I'm sure there's questions.
You mentioned positron emission tomography as an application in the middle of the talk. I missed the time resolution, which can be achieved there. This may be a clue in order to locate the longitudinal position of where the positron was annihilated. Would it be good?
So the time resolution is in the order of 100 picoseconds. Yeah?
It is also for this application?
No, I mean the time resolution on PET, there's the problem that the scintillator you have, the LYSO, has a decay time of 40 nanoseconds. That is the big problem. The material is not fast enough. If you do plastic, it's much faster. If you do Cherenkov, it's much faster. But to measure the depth from the arrival time of the photons, I think there's no way. People are doing time of flight now, where the time resolution of 200, 300 picoseconds is already helping you, but not for depth of interaction. By the way, Philips company, they have, 10 years ago, they have funded this PDPC company, and they did exactly the same. These are CMOS detectors. They had their own little technology from Philips, optimized for good spot quality. They didn't give access to anybody. And the PET scanners you can buy from Philips, they are actually using CMOS photodetectors at the moment.
But not what you are doing.
Not what we are doing.
Also on the LYSO crystals, when you were showing your event displays, you were seeing the singular rod, but also some pixels were firing close to that. There was some sort of a noise that was correlating to the...
Of course. I mean, the segmentation of these crystals is very difficult. So there's a reflective foil in between, which is not perfectly reflecting. And the way when they do it, I think they first cut slices, they put the foil, and then they cut it again, and they put another foil so the light can creep through. But it's true, there is a lot of optical crosstalk, and we have not further studied this in much more detail. There's one more problem, that the crystal is standing on the chip, but the chip has quite a thick optical layer on top before you come to the spots. So it's like 4 or 5 microns, so the light can travel around, and we see actually really light going very far because the chip acts as a light guide. So this should be studied, yeah. I have a student now looking at this old data, yeah, trying to at least check if the Compton rate is what Jean tells us.
Yeah, you said low power, low cost also, so what sizes can you achieve, and are you competitive, let's say, for the application of the fiber tracker with this more standard way of reading it?
Yeah. So this is a difficult question. So the first question is the reticle size is 2 by 2 centimeter. Yeah, so you could make chips of this big size. Then the price of a wafer, this is an old-fashioned 350 nanometer technology, unfortunately. Yeah, so I cannot really compete with high-speed stuff. This is old-fashioned technology. But the price of a wafer is what the typical price of a wafer is, 2,000 euros or so, in mass production. Yeah. So if a physics group would do it and order the wafers there, and they go with it, yet they do it, it's not clear if Fraunhofer would do a mass production. Yeah? That's their political decision. There is no Hamamatsu company in between, basically. Yeah, so it's like you order the wafers for pixel detector, then the price of the chip is cheap. You have more to compare to the price of the electronics chips, because then you're done. Yeah? It's a difficult question, because at the end they also want to make some money. But I claim it should be cheaper. It's half the number of components, and if we organize it ourselves, there is no company in between.
Yeah.
With these batteries, the large batteries, how do you make sure, and when you want to do one electron detection, photon detection, how do you make sure that you stay away safely from the excess noise of the avalanche productions?
Yeah, what has excess noise?
Yeah, when you have noise coming from fluctuations in the avalanche process.
This is Geiger mode. So
That's always
this is always Geiger mode.
That's always
It's Geiger mode. Yeah. So the Geiger mode means the voltage is so high that the avalanche would burn forever. It would just go crazy.
You mentioned a gain of 30.
And you need and you need a mechanism to bring down the voltage so that the avalanche stops. And this is done by this quench resistor, like in the Geiger detector. Yeah. So there is always this number of gain. The gain of these devices is not 20, it's 10 to the 6, 10 to the 5 or 10 to the 6. It's just one electron charge going up to a 2-volt signal on a 50 femtofarad capacitance. And you can divide it, and it's no, it's not low gain. It's very high gain. Sorry. Yeah.
The crosstalk which was seen, was it light crossing from one of the fibers to the next, or was it, say, crosstalk inside or between spans, where you have at the high gain also some crosstalk within the center?
So we know the crosstalk, there is when one spat fires, yeah, then you have plenty of electrons being produced in the avalanches, and there are also photons created in the avalanches, and these photons can travel to neighboring spots. And we can measure the crosstalk very easily with these chips, and it's in the order of 3 to 4% of optical crosstalk only, so it's very low. So this crosstalk we see, which is much more, must be from the setup, from the fibers, and so on. We are careful, the fibers don't really touch, yeah, so the fibers are in some distance still, as much as we can do it with a plastic 3D printer, yeah, to make sure we don't destroy anything. So I'm sure this can be improved. Normally, you would glue the fibers on the chip.